Det är vår kultur. I alla fall så kan det inte vara några svårigheter på vad man kommer fram. Jag såg det var mer snygg på det. Jag starten snabbt och en svår Välkomna till Kungliga Vetenskapsakademin och den här presskonferensen då vi ska presentera årets Nobelpris i kemi. Welcome to the Royal Swedish Academy of Sciences and this press conference when we will announce this year's Nobel Prize in Chemistry. We will keep to our tradition and start in Swedish and then continue the presentation in English. And you are of course welcome to ask questions later on in either of these languages. Jag heter Hans Ellegren och är ständig sekreterare här vid Kungliga Vetenskapsakademin. Till höger om mig sitter professor Johan Åkvist som är ordförande i Nobelkommittén för kemi. Och till vänster om mig sitter professor Olof Ramström, också ledamot av Nobelkommittén för kemi och sakkunnig inom ämnet. My name is Hans Ellegren. I'm the Secretary General of the Royal Swedish Academy of Sciences. And to my right is Professor Johan Åkvist, Chair of the Nobel Committee for Chemistry. And to my left, Professor Olof Ramström, member of the Nobel Committee in Chemistry and one of the experts in the field. Årets pris handlar om ett funktionellt sätt att bygga molekyler. This year's prize is about an ingenious tool for building molecules. Kungliga Vetenskapsakademin har idag på morgonen beslutat att utdela 2022 års Nobelpris i kemi i lika delar till Carolyn Batuzi, Stanford University, Kalifornien, USA. Mårten Meldal, Köpenhamns universitet, Danmark. Och till Barry Sharpless, Scripps Research, La Jolla, Kalifornien, USA. Det tilldelas priset för utveckling av klickkemi och bioorthogonal kemi. The Royal Swedish Academy of Sciences has this morning decided to award the 2022 Nobel Prize in Chemistry in equal shares to Carolyn Batuzi, Stanford University, California, USA, Mårten Meldal, University of Copenhagen, Denmark, and to Barry Sharpless, Scripps Research, La Jolla, California, USA. They received the prize for the development of click chemistry and bioorthogonal chemistry. Professor Åkvist will now give us a short summary in English of the prize. Please, Johan.
Thank you. Click chemistry is almost like it sounds. It's all about snapping molecules together. Imagine that you could attach small chemical buckles to different types of building blocks. Then you could link these buckles together and produce molecules of greater complexity and variation. This was the basic idea behind click chemistry that Barry Sharpless had about 20 years ago. The problem was to find good chemical buckles. They have to react with each other easily and specifically. Mårten Meldal and Barry Sharpless independently found the first perfect candidates that will easily snap together, and importantly, they won't snap with anything else. This click chemistry can now be used for building drug molecules, polymers, new materials, and many other things. However, there are also other reasons for why one likes to snap molecules together. Imagine that you could attach a shining molecule to biomolecules in a living cell. Then you could follow them in a microscope and see where they are and how they move. This is what Carolyn Batuzi did, but she had to find click reactions that were not toxic to the cells. She called this bioorthogonal chemistry. Chemical reactions that don't interfere with the normal biochemistry of life. This now allows us to attach all kinds of molecules to biological ones, which can be very, very useful. Besides tracking biomolecules, it can also be used for diagnostics, for delivering drug molecules to their targets, and many other applications. So this year's laureates founded the fields of click chemistry and bioorthogonal chemistry. It has led to a revolution in how chemists think about linking molecules together and how to do it in living cells. Thank you.
And I'll leave the word to Professor Olof Ramström, who will give a more detailed presentation of the prize. Please, Olof.
Thank you so much, Hans. Thank you, Johan. So this year's award is, as Johan just mentioned here, it's about making connections between molecules in a very straightforward, selective, and robust way. This year's award is also about concepts and how concepts combined with very important discoveries really push the boundaries and make enormous impact of science and our society. So let's start with the first concept. Around the turn of the millennium, Barry Sharpless presented a new concept which he called click chemistry. And by this, he meant chemistry that was based on very special reactions that work very efficiently, were very reliable, and gave very robust products, very robust yields of products. By this type of chemistry, like Johan here said, you would be able to essentially click together two molecular building blocks in a very efficient way, in a very predictive way, and you will get a good amount of product in a very reasonable short time. Now, such reactions were not very common or very difficult to find. But one such reaction was just about to be discovered. And very shortly after this click chemistry concept was introduced, Morten Meldal and his group in Denmark, and very shortly after, Barry Sharpless and his co-workers in the US, they found one such reaction that is really remarkable. This reaction is based on an A-side functionality, as you can see to the upper left here. This is a structure which has 3 nitrogen atoms in a row. And the opposite candidate here, the opposite reactant, as we call it, is an alkyne, as you can see to the right. And this alkyne is a kind of structure where you have 2 carbon atoms that have 3 bonds between them, a triple bonded carbon. Now, these 2 reagents, these 2 building blocks, they are not terribly reactive by themselves. And if you mix them together, they will react very sluggishly with one another. And also, they will give mixtures, very often give mixtures of products. So not very good. However, what Meldal's group and Sharpless and co-worker found out was that if you add a little bit of copper 1 ions to this reaction mixture, the reaction was dramatically accelerated. And also, it only gave 1 single product. And the product is this ring-shaped, 5-member ring-shaped product called a triazole. And again, this product is also quite unreactive product, quite stable product. And it also has other interesting features that could be of interest. So in a sense, as you can see here, this particular reaction fulfilled the criteria of click chemistry. And now you had a tool where you can easily click together molecules in a very effective way. Immediately upon discovery of this reaction, this reaction is called, as you can see down here, the copper-catalyzed A-side alkyne cycler addition reaction. Immediately upon its discovery, it gained enormous interest across chemistry and related fields, and immediately spread across all fields. And now, with this reaction, it was now essentially although other reactions have been, so to say, identified and discovered after this one, this particular reaction has almost become synonymous with the click chemistry concept and is also often called the click reaction. And you can say that it's still the crown jewel of click reactions. And with this reaction, it's now possible to build together relatively complex structures, as the one you can see here, where you can click together multiple components, multiple building blocks, click them together in sequence or in parallel, giving rise to, in this case, a star-shaped complex molecule, dendrimer-type-like molecule. Now, one of the areas where people wanted to apply this reaction was in biology or biochemistry related areas. But for this reason, in these cases, when you work with living cells, copper is not ideal, and living cells don't really like too much copper. So for this reason, alternative reactions were sought after. And that brings us to the second concept. Around the same time as the click chemistry concept and these copper-catalyzed click reactions were introduced, Carolyn Batuzi formulated a concept which she called bioorthogonal chemistry. And by this, she meant chemistry that is based on special reactions that can be performed in living systems, in living cells, in living organisms, without affecting or being affected by the myriad of substances and reactions that occur in such very complex systems. As you can imagine, this is definitely not an easy task. So during the 1990s, Carolyn Batuzi had been trying to work out the chemistry and biology of complex carbohydrate structures, complex sugar structures that are called glycans, and they are often located at the surface of cells, as you can see in this picture. Batuzi and her group had been identifying chemical reactions that could work in living systems, in living cells. For example, they had identified a way to introduce the A-side functionality in living cells and living systems. And they could do so by a type of metabolic engineering approach, where you have a sugar structure, a carbohydrate structure, which is then functionalized with an A-side moiety. And when you grow cells in the presence of this structure, this can be taken up by the cells. It can go through and be processed by the cell machinery, and finally become incorporated in the glycans that you find at the cell surface, as you can see here. Now, once this fantastic copper-catalyzed click reaction had been discovered, shortly after, Batuzi could also identify a metal-free alternative. And you can see the alternative here. And this alternative was based on a so-called strained alkyne, as you can see. This is an 8-membered octagonal alkyne, where the alkyne's moiety is actually twisted in a sense that it becomes much more reactive. And this alkyne structure, you can then, of course, functionalize any way you want. In this case, for example, with a molecule that can emit green light. And if you then add this strained alkyne to the cells where you have this A-side functionality, these two components can click together very efficiently, and now you have labeled the glycans at the surface of the cell, and you can study where they are under the microscope. And that's exactly what you can see on the next slide here. Here you see a number of cells, and the blue part here is the cell nuclei that have been labeled blue. And you can see the green, shining green surface of the cells where you actually have those glycan structures. So these two concepts and the reactions that have been, so to say, discovered they have really had an enormous impact on science. And there's many widely applied across all disciplines of chemistry and related sciences, neighboring sciences. Click chemistry, if you take click chemistry, has been applied almost everywhere. You need to very quickly connect two building blocks. For example, just to give you a few examples, it's been applied to pharmaceutical development, it's been applied to conjugation of various biomolecules, such as, for example, in DNA sequencing. It's also been applied, very much applied in material sciences, where people have been building very advanced and functional materials using these methods. When it comes to the bioorthogonal reactions, these have been heavily used to explore how biomolecules, the fates and the roles of the biomolecules in cells and in organisms. They have been used to study disease and deciphering disease processes, and of course that can then lead to the development of new drugs. And in a little movie you can see here to the bottom left here, we have one such example where you can see a bacterial cell. You can see the cell envelope is marked in green, and inside this bacterial cell, one of the proteins has been labeled using this kind of chemistry, and now you can follow it in real time inside the cell. So clearly, these very important accomplishments and these really fantastic discoveries from our three laureates have really made an enormous impact on chemistry and on science in general, and for that, it's really been to the greatest benefit of humankind. So, thank you.
Thank you, Olof. Det sa bara klick, as the Swedish quote often is said. Now we shall see if we have one of the laureates with us. Professor Carolyn Batuzi, are you there?
Yes, I'm here.
Congratulations for receiving the Nobel Prize in Chemistry.
Thank you so much, all of you. I'm absolutely stunned. I'm sitting here, I can hardly breathe.
I understand. It's the middle of the night for you. Was it a shock to obtain this call in the middle of the night?
Yes, that's an understatement. I'm still not entirely positive that it's real, but it's getting realer by the minute.
Yeah, it will probably be a long night for you today, I guess. We shall see if we have some questions here. I'm sitting in the session hall of the Royal Swedish Academy of Sciences, and we have many interested journalists here, both from the international press as well as from Swedish press. Are you ready to take some questions?
Absolutely. Hello, everyone.
Okay. SVT?
Good morning. Congratulations. This is Swedish television, public service. Thomas von Heine. We heard something about applications from your work. Could you say something? Could you add something to that? What, in your mind, the most interesting applications?
Absolutely. To my mind, the two types of applications that I think are really making a lot of impact are, first of all, the use of bioorthogonal chemistry as a biological discovery tool to discover new kinds of biomolecules that we didn't even know existed because we have a new way to look at them. And then the other important area of impact is in medicine, and in particular for drug delivery, which is doing chemistry inside human patients to make sure that drugs go to the right place and stay away from the wrong place.
Okay, I think first we had a question here somewhere.
Congratulations, I'm Anneli Megner-Arn, Swedish TV4. I wonder if your click technique was involved when we were developing the antibody test of COVID-19?
That's a great question. We did some research in my lab around not so much diagnostic tests, but development of potential therapeutics to treat acute COVID-19. And we did use click chemistry and bioorthogonal chemistry in putting together some drug prototypes.
Okay, a question in the back there.
David Keaton from the Associated Press. First of all, when we look at click chemistry today in 2022, what are the areas of new developments that you're the most excited about, the new discoveries? And if you could maybe explain in layman's terms what this really means to chemistry.
Thank you for a great question. I think the field of bioorthogonal and click chemistry is still, I think, in its early phases. We have a handful of incredible reactions like the ones that Professors Sharpless and Meldahl developed. But it's really just a handful. And I think there's probably many new reactions to be discovered and invented. So that's an important frontier, is inventing new chemistry. And then in terms of applications, again, I think applications in the biotech industry, the pharmaceutical industry, and the development of new ways of treating diseases and diagnosing diseases, I think that these are areas that will be very strongly impacted by click chemistry, as they already have been.
Okay, question here, please.
Congratulations, Professor. Click chemistry is a very effective and useful method for building molecules. So my question is it easy to scale up the reaction?
Yes. In fact, I think that's one of the most elegant features of click chemistry reactions, is the fact that they're so simple and they're so highly selective that the yields tend to be very high with very little impurities, and that makes them very nicely scalable. And in fact, click chemistry reactions are already being performed at manufacturing scales in the pharmaceutical industry.
Okay, we have time for more questions. Oh.
Thank you. Pardon me, Philip O'Connor, the Reuters News Agency. Congratulations, Professor. I'd like to ask you, was there a specific question that you were seeking an answer to when you set off down this path? And did you find the answer, or did you get answers to different questions in your research?
This is a great question. And the answer is yes and yes. And just to give you a little bit more detail, what set us down the path of developing bioorthogonal chemistry was an interest in being able to visualize molecules on cells that no one had been able to see before. And those molecules for us were the glycans. And once we figured out how to visualize the glycans using those chemistries, we learned all kinds of interesting things about the functions of glycans that coat the surfaces of cells. And what we learned led to the development of a new idea for cancer immune therapy, and at the same time also led to the discovery of a new kind of biomolecule called glycoRNA that had never been seen before. Does that answer your question?
Okay, one more question here.
Associated Press. Obviously, this prize comes with an incredible notoriety and also prize money. What do you think this notoriety will bring and this prestige will bring to this area of science, to yourself, and then obviously, what are you hoping to do with this, the prize money that comes with this?
I can answer your questions in reverse order. I haven't had enough time to think about the prize money, so I don't know yet. But then to your earlier questions, I think that the attention that a prize like the Nobel Prize brings can be incredibly energizing for a scientific field. And I've been very fortunate to work at the interface of chemistry and biology. It's such a rich interface with so much great technology development and fundamental basic science discoveries. And so to the extent that the prize casts a light on chemical biology, I think that's a wonderful thing. I think the other incredible benefit is that it's an opportunity for me to recognize all the work that so many trainees from my lab have done over the last 25 years. And I've been very blessed with an incredible team of graduate students and postdoctoral fellows and undergraduates and staff. And it's an opportunity for me to reflect on how fortunate I have been and to share in the celebration with them.
This seems to be the last question from the press for you, Professor Batuzi. Thank you, and once again, our warmest congratulations for receiving the 2022 Nobel Prize in Chemistry. We look forward to see you here then in Stockholm in December then.
Myself as well, and thank you so much.
Goodbye, goodbye. Let's move on to see if there are some questions here to the committee about the research or the prize. We have one more here directly.
Yes, a question about the comparison between last year's prize and this year's prize. Both dealt with new ways of building molecules. Is that correct? Could we say that there are bridges between these two prizes, or is that not the case?
Would you like to?
Well, they are separate areas, of course, but you're perfectly right in that it has this ingredient of different new ways of building molecules. Although last year's prize was maybe more a pure organic chemistry prize, as you have heard, this year's prize spans very big application areas in chemistry. So, but it's about building molecules and attaching molecules to each other.
More? Yeah, please.
This is Dongkun from Nordic Chinese Times. And again, one question is click chemistry a good method for conducting framework materials like MOF, metal organic frameworks?
Olo?
Well, that's an interesting question. And actually, I think it has been applied to that particular field as well. So you can introduce either the acide or the alkyne group, if you use that reaction, in this these organic frameworks that you're referring to. And then you can just click on the other reactant, and then you have a way to functionalize these frameworks very easily and straightforwardly. So yes, it has been used like that.
Are there any more questions? If not, we say thank you for your interest. We hope to see you back here in the Academy on Monday when we will present this year's Sveriges Riksbank's Prize in Economic Science in memory of Alfred Nobel. Thank you.
Professor Olof Ramsten, a member of the Chemistry Prize Committee. This Click Prize, what is it about? Can you please explain?
This is a fantastic prize. This is a fantastic prize to fantastic discoveries, I should say, that our 3 laureates have made. And they have been working on methods to try to connect molecules, connect building blocks, and they can be clicked together very simply and straightforwardly. And essentially the same way as you build Lego, right? So you can have the Lego pieces and you can just click them together and you can build very advanced, houses or tools or vehicles, even spaceships you can build using that. And the same is the same with this chemistry, although at a very, very, molecular level, so to speak. Everything is very small, but you can click them together and you can build very advanced structures in a very simple and straightforward way.
And why has this been so difficult before?
Well, it's very difficult to find such means or such reactions, as we call them, to actually do this. Because if you want to have a reaction that can be really just work every time you use it, just clicking together every time you want to use it, and you get predictable products, you know what you will get. That is really difficult to do. Right? So there are not many reactions like that, and we only have a handful of such reactions today.
And what do you build with those click things? I mean, what could it be used for?
The funny thing, the good thing with these discoveries is that it can be used for almost everything. So it's been spread very widely. And it's been used where you, for example, make new drug compounds, to treat illness and so on. It's been used to make all sorts of different materials, like polymers, like gels. It's hard to explain what those mean. but you can make almost everything where you just want to click together things, right? You can build very advanced structures that can be used to deliver drugs in the human bodies. You can use them for almost everything you can think of.
And why did you decide to give the prize right now? Why is this moment?
Well, that is always a very difficult question to answer. But the way we work normally with many different areas at the same time. And in this particular case, this field has now matured in such a way that we now think it's ready for this kind of award. So now we have all the pieces of the puzzle together, you can say. So now we just know that exactly the last piece of the puzzle came in, and now we see that the whole picture is perfectly fine. And we have now a very fantastic new award, as we can say.
It's about time, you say?
You can say it's about time.
So tell us a little bit about the laureates. One of them, Barry Sharpless, he got the Nobel Prize 2001. Is this common?
This is not at all common. This is not at all common. It happened a few times before in the past that certain individuals are really, really, really creative, and Barry Sharpless is one of those. So he got the Nobel Prize in 2001 for a relatively different area. And now, after that, he has continued working on other things, for example, this thing. And he made such important discoveries in this field. So you have to say that he is a really creative person, and he deserves now this second award.
We just heard another one, Carolyn Batuzi on the phone. Could you tell me about the reaction when you called her?
Well, I cannot say too much, but we can say that when we call the laureates, they are always very, very happy. They're almost always very surprised, and it's a very emotional moment when we call them all the time, every time.
Are they related? I mean, do they have they been working together on this? Do they know each other? Could you tell us?
I am absolutely convinced that they know each other, but I do not think that they have actually been working directly with one another. Might be. I'm not absolutely certain about that, but definitely know each other because these discoveries and the concept they have come up with, they are very connected, and so I'm sure they definitely know each other in that sense.
Tell us a little bit about Carolyn Batuzi. Yeah. Who is she? And
well, Carolyn is a fantastic scientist, a fantastic woman that has been actually revolutionizing the way we can analyze or visualize and even how to say see certain molecules in the living body, right, in living systems. So in, for example, the human body, we have tons of different carbohydrate sugar structures, but they are very difficult to see or to find out what they're doing. And that's exactly what Carolyn Batuzi has been, focusing on. She has been trying to really figure out exactly what these sugar structures are doing, where they are in the body, in the cells. And she has come very far using this chemistry that she has developed, using this type of,
The click
type of chemistry that she has developed.
She also said it was connected to COVID-19 research in some way.
I mean, it's very natural that if you have these kind of tools that she has developed, and then of course we had this pandemic, they were also looking into if they could actually use those tools to make new, therapeutic agents, drugs against this terrible, virus. And as we heard her saying, also they managed to do something. For example, antibody-drug conjugate, I think they mentioned, which may be used as a drug against this virus.
Click chemistry, it sounds simple, but how many years has it taken to develop this tool?
It's depending on where you start the process. So click chemistry is the concept of this field, so to speak, the name click chemistry has been around for around 2 decades. Right? So it's not terribly old, but it's of course resting on other discoveries that were made earlier. So in that perspective, in that sense, it's a much older chemistry. So it took a very long time to find this fantastic click reaction that really works every time, that really can be used everywhere under all different conditions. So it's a fantastic discovery, these click reactions.
What do you think would be the future applications of this?
Well, I think we have already seen a lot of applications already, and I think in the future we will see they will become more mature. There will be more products on the market for our benefit. For example, different materials that we can use, different drugs, as we have mentioned. They can be, we can use them for curing disease or at least treating disease. And we can have, for example, there is examples where you can make materials where you can grow cells. For example, if you have a damaged ear, you can grow a cell and then you can graft it onto the ear using this methodology. And then so there are many, many applications. I think in the future we will see so many more that directly has a benefit to us humans as humans.
So finally, if you would have 30 seconds to say why you are so enthusiastic about this, what would that be?
Well, I think this is a fantastic award for many reasons, and one of the reasons I think it's such an interesting combination, because it's very clearly, 2 decades ago when this first reaction was discovered, that there was absolutely in the scientific world, there was an unmet need. There was really an unmet, absolute huge need. And when this reaction was discovered, it was like opening the floodgates. So everywhere, all the time, this reaction was applied. They were using it everywhere to build everything, right? So that is definitely what I thought.
Thank you very much, Professor Olof Ramström. Thank you very much.
Thank you so much. Thank you.